Hi all, welcome to the talk. Today I'll be talking about finding perfect matchings in bipartite hypergraphs. I'm from ET at Zurich. I didn't take this picture, however, and actually the work I'm going to show you today was when I was at EPFL. Unfortunately, you will have no more nice pictures in this talk. So the object of today's talk is this notion of bipartite hypergraphs. So most of you know what a hypergraph already is, but let's just go over the definition. It's just a set system consisting of a ground set of elements V and a collection of subsets of this ground set, which we call edges. And now we are interested in bipartite hypergraphs, where the hypergraph has additional structure. So in particular, the vertex set of the hypergraph is partitioned into two sets, where each edge in the hypergraph has exactly one vertex from one set and r minus 1 vertices from the other set. Now, that's the definition. Immediately, I want to point out that this definition is asymmetric, so we distinguish one of the bipartitions in our vertex set, okay, from which each edge will have exactly one vertex, and call that the A set. Okay. So what are we trying to find in this bipartite hypergraph? So it's a perfect matching. Again, a definition familiar to most of you here. It's just a collection of edges that are vertex disjoint. And the property that each vertex of A is contained in some vertex of the matching. So then we call that a perfect matching. Okay. So we all know that for the r equal to 2 case, we have bipartite hypergraphs, for which there's a very nice necessary and sufficient condition for the bipartite hypergraph to contain a perfect matching. This is called Hall's condition, and many known proofs of Hall's condition also supply a polynomial time algorithm to find this perfect matching. So I just made a small picture here. If you have a perfect matching as indicated here with the red edges, and let's say one vertex is still not matched, then you construct this alternating tree starting from that vertex, trying to find an augmenting path. So in this case, it would be this path here. By the way, if you have any questions at any point, please feel free to stop me, because the presentation is fairly short. Okay. Okay. So this approach was so this is the basic augmenting path algorithm. You try to find as many augmenting paths as possible until you reach maximum matching. This approach was improved by Hopcroft, Karp, and Karzanov to give a better algorithm. And we also have later results by Lovász, Mucha, and Sankowski based on connections to matrix multiplication, and most recently the work of Madri, which shows faster algorithms for finding maximum matchings in certain kinds of bipartite graphs. Okay. So we can ask the same question also for the r greater than 2 case. So can we hope for efficient algorithms for finding perfect matchings in bipartite hypergraphs? The situation is somewhat similar to the jump in complexity from 2-sat to 3-sat and many other cases. So the answer is no in general, because, then P would be equal to NP. So we sort of rephrase this question in a different way. So there is a non-constructive analog of Hall's condition for this class of bipartite hypergraphs. So in particular, it's a sufficient condition, which states that if a certain condition is true, then there is a perfect matching in that hypergraph. So we could aim to constructivize this result, and this would not violate any well-known complexity theoretic assumptions, okay, hypotheses. So what is Haxell's condition? So it's a theorem from 95 by Haxell, which states the following. Okay, so if for every subset of vertices in the set of vertices A, this condition is satisfied, then the hypergraph admits a perfect matching. So what is this condition? So given a subset of vertices S, then consider the collection of all the edges in your hypergraph that are incident to some vertex in the set S. So this is a sub-collection of the edges. And now what is the fewest number of vertices from the B side that you need to hit all of these edges? By hit, I mean, So a collection of vertices hits a collection of edges if each edge contains at least one vertex from the collection. Okay. So here is a picture. This is the collection of vertices that I've chosen to be in the set S, and this is the collection of all the edges that are incident to these two vertices, and the fewest number of vertices from the B side that you need to hit all of these edges is 3. Okay. So notice that there is a strict inequality here. So tau of S is strictly more than 2r minus 3 times S minus 1. And actually this condition is tight in the following sense, that if you replace this condition only by a non-strict inequality, so if you had the hypothesis that tau of S is at least 2r minus 3 times S minus 1 for each subset in A, then it is no longer necessary that there is a perfect matching in the hypergraph. So let's see the example, which is nice. So there are just 2 vertices on the A side and r minus 1 squared vertices on the B side. And what are the edges in this hypergraph? So each vertex of A is contained in an edge of the following kind. Pick one vertex from each row. And each vertex of, the second vertex of A is connected to, is contained in edges of the following kind. Pick some row. Now it's clear that there is no perfect matching in this hypergraph. And you can check that this satisfies Haxell's condition with non-strict inequalities. For S equal to 1, this is easy. For S equal to 2, so you take both of the vertices here, consider all the edges that are present in the hypergraph now. What is the least number of vertices that you need to pick from the B side so that all of the edges are hit? So this is, if you think for a moment, you are forced to pick some row and some column. And so that's r minus 1 plus r minus 1 minus 1, which gives 2r minus 3. So, okay. I thought I would include a slide on how exactly we arrived at this problem. And we were studying this a class of allocation problems, and in particular this problem where you have a bunch of resources and a bunch of players, and the goal is to partition the resources among the players so that the value received by any player is as large as possible. Okay. So in this case, each resource has a value, and each player is interested only in a subset of the resources. So for example, the person here is interested in money while the animals are not interested in money. Just to go over the objective function again, the objective is to partition the resources among the players so that every player receives at least value t, and t has to be as large as possible. So this is a very natural fair allocation objective. And this is called the restricted maximum fair allocation problem, for which we gave a 13 approximation algorithm. And the techniques we used to prove this algorithm were actually completely combinatorial. And so there was this question whether these techniques would apply in the more abstract setting, if you want, of just hypergraphs. So without referring to the configuration LP or values of the resources and so on, and other approximation related stuff. So we pose this as an open question, that if you assume a stronger condition than Haxell's condition, now can you find this perfect matching in this hypergraph? So it's guaranteed to exist. Can you find it? Okay. So our result is that it is indeed possible, and it is possible in a certain strong sense that you only need to have a small strengthening of Haxell's condition. So you don't lose much in the sufficient condition. And yeah, so this is one formulation of the theorem. So let me just read it to you. So for each fixed choice of epsilon and r, so you fix r and you fix epsilon, there is an algorithm that depends on epsilon and r, and it takes as input r uniform bipartite hypergraphs. So the size of the number of edges and the number of vertices are now the varying parameters. And all of these hypergraphs, they satisfy this condition. So then the algorithm is guaranteed to find a perfect matching and terminate in polynomial time. Now, one thing is we don't know how to check Haxell's condition itself or this condition itself in polynomial time. So I thought I will just make a small reformulation of the result that the algorithm actually runs on any R uniform bipartite hypergraph, and it does one of two things. So either it outputs a perfect matching, or if it cannot, it actually outputs a set that violates this hypothesis that we assume. Okay. Yes, 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 yeah. Not the best hitting set, but one hitting set, yeah. So the algorithm as it is written in the paper currently does not actually output such a set, but it's clear if you see the analysis that it can just, yeah. Okay, so I'm just going to state the algorithm and give an outline of the analysis, and that will be the end of the talk. Okay. So the algorithm is an augmenting algorithm. So just let's recall what an augmenting algorithm is. So we start with a partial matching in our hypergraph. So a partial matching is just a matching, but we use partial to emphasize that it is not perfect. And also an unmatched vertex A0. So some vertex in A that is not contained in one of the edges of the partial matching. And this is the input to the algorithm. And then the output will be a larger partial matching. And so the algorithm I'm going to present to you is an augmenting algorithm. And what it will do is construct an object very similar to the alternating tree for bipartite graphs, and except now it's slightly more complicated. So this is the alternating tree, and let me just make a few observations here. So first, the algorithm places the unmatched vertex at the top. So A0 is at the root of this alternating tree, and you can see that the edges of the hypergraph that are present in this tree are alternating, right? So there are blue edges and red edges and blue and red. So it's sort of convenient to split this alternating tree into layers. So you have layer L0, L1, L2, and so on. And also the vertices that lie on this black lines are always the A vertices, and the vertices that lie here are always the B vertices, okay, just so that we are on the same page. And notice, so the main difference between the bipartite case and the graph case and the hypergraph case is that a single edge, so I also call blue edges to be addable edges and these red edges to be blocking edges, and these red edges always come from the partial matching, if you recall. So the main difference between the graph case and the hypergraph case is that a single addable edge can now intersect up to R minus 1 blocking edges. So imagine that we had an edge in the hypergraph which did not intersect any edge from our partial matching, as was the case, no, not the case here. Then you would be immediately done. So in fact, the main operation, which is a very simple one, is just going to be swaps of the following kind. So this unmatched vertex will want to take this addable edge, but then he's blocked by this partial matching. So we recursively try to find another addable edge for this vertex, and there exists one, so then this gives a kind of path. Okay. So let's go into the details. So assume that you have constructed L layers of the alternating tree. So initially L will be 0, and the only vertex will be the root vertex. Then we will build layer L plus 1 in the following way. So order the vertices that are contained in the blocking edges of the previous layer in some fashion, and try to check if there is an edge in the hypergraph containing this first vertex and disjoint from all the vertices before in the alternating tree. Okay, so we find one, and it might happen that this hyperedge actually intersects with some new edge in the partial matching that was not already present in the alternating tree. So then we put all such blocking edges into YL1, and this addable edge will be added to XL1. So I didn't mention before. So each layer contains addable and blocking edges which we put in XL and YL. Okay. and then we repeat that operation again for the same vertex. So we try to find again a new hyperedge containing this vertex, disjoint from all these vertices and also the vertices before in the alternating tree. If there is one, we add it, and potentially it is also blocked by some additional edges in our partial matching so far. And we repeat this process for this vertex, obeying a degree bound. So this is just some constant when you think of r and epsilon as fixed numbers. So we don't want to add too many hyperedges for this single vertex. And then we repeat the same operation for each vertex. And this completes the build step. Notice that it can happen that we add a hyperedge for which there is in fact no edge from the partial matching which is blocking it, so which is intersecting it.
So you do this only for all vertices satisfying the degree bound, or for every vertex you restrict the number of addable edges?
Yes, yeah. We restrict the number of addable edges for each vertex to be at most 10 r squared over epsilon squared. So we do this because if you think about it, this operation is dependent in the sense that if this vertex claims a lot of hyperedges, then potentially this vertex cannot get any more hyperedges because the first vertex claimed a lot of hyperedges. So in some sense, all progress in further layers will be focused on just removing the blocking edges for the addable edges for this particular vertex. But we want it to be more balanced. So we impose that a certain vertex cannot claim too many edges. So this is the reason why we have the degree bound. Actually, any other restriction or constraint which ensures a more balanced allocation or a more balanced building of this layer will also give similar results, but just the simple upper bound suffices. But it could be interesting to look into this. Okay, so we build this, and now we check one. So if this condition is satisfied, now there could be many such addable edges in this layer. So now Haxell plus 1 contains all these addable edges. So we call this edge an immediately addable edge, which means that we can now swap this edge, which is not in the partial matching, with some other edge that was in the previous layer, which is in the partial matching. We can perform a swap operation. Now, if there are more than mu fraction of Haxell plus 1 which are of this kind, then we perform what is called a collapse operation, okay, which I'm going to show you on the next slide. If, on the other hand, there are very few edges of this kind, then we continue to build the next layer and keep going iteratively. So let's see what happens when there are a lot of addable edges which are not blocked. Okay. So by the way, mu is just a constant, again, depending on r and epsilon. I don't mention it because it's not important for the talk. So in this case, we just swap the blocking edge in the previous layer with the addable edge that is immediately addable. Okay, so we do this for all the vertices here that are having some immediately addable edge. Notice that a particular vertex can have up to u immediately addable edges, so just pick any one for the swap operation. So once you do this, you just discard this layer LL plus 1, like completely throw it away, because we were able to reduce the number of blocking edges in this layer LL. So we reconstruct, sorry, that was a question now. So we reconstruct the layer LL plus 1 after performing this operation. Okay. But now there is one small catch. Notice that when we built layer, so we now make changes to layer LL. Notice that when we built layer LL, maybe this vertex could not take additional edges because this blocking edge was present and this vertex intersected with some edge he could have otherwise taken. And now, because of this collapse operation, these edges actually disappear. So now it might become possible for these vertices to actually take additional addable edges because of this operation. So we have to be careful. And so we check, so we perform what is called a superposed build operation. It is nothing but performing the build operation on layer LL given this state. So we normally perform build operations given the empty layer, and now we perform the build operation given this state. So we go from each vertex and check if we can take an additional addable edge that is disjoint from all the vertices in the tree, and we also respect the degree bound. So we do that for each vertex. Do I? Yes. So here we do a collapse operation on layer LL plus 1, and we completely remove LL plus 1. I would collapse again if in layer LL again the removal of these blocking edges makes mu fraction of XL immediately addable, in which case it will be recursive. So we will in fact always have the invariant that at most mu fraction of the addable edges in any layer are immediately addable at any point in the algorithm. Okay, and that is the algorithm. So it always alternates. One thing I forgot to mention is so after performing the superposed build operation, there are newly introduced addable edges for some of these vertices. Now we add those edges only if the increase in the size of XL is mu fraction. So if they are very small, then we don't change the state of the alternating tree. Now this is not very intuitive. It will become intuitive if you know what the analysis is. So the analysis is based on finding how many changes to the alternating tree we make. So each time you perform a swap operation, you change the state of the alternating tree. And the analysis is basically saying that the total number of alternating trees that you encounter is only polynomial. So given that this is how you are going to analyze the algorithm, you don't want to make too many changes to your alternating tree, because that is going to give us the upper bound. So that's why we make changes only if we can make a large change. Okay. So that is the algorithm. We always alternate between build and collapse steps, and collapse steps are always recursive. You collapse until you cannot. Okay. So let me just give a very simple outline of the analysis. It's actually a very short paper, so you can have a more detailed look if you would like. So the first thing we prove is that the height of the alternating tree is logarithmic. So this means that it doesn't take very long before you find augmenting paths, so to say, in the hypergraph case. And the way we show this is by saying that whenever you build a new layer L plus 1, then the number of addable edges in that layer is at least a constant fraction of the total number of blocking edges you've seen so far. Now assume that 1 minus mu fraction of these addable edges are actually blocked. Like this is sort of the bad case, right? So that means YL plus 1 is at least 1 minus mu times this constant times Y at most L. And we also know that each player that is in the alternating tree is contained in a unique blocking edge. So in particular, the sum of the cardinalities of all these sets Y is at most the total number of A vertices. And the sums are also, so if Yi is at least constant times Y at most I cardinality, and the sum is bounded, then this is logarithmic. So L is in particular logarithmic, so this is easy. And next what we do is so the idea I alluded to earlier, you have a alternating tree, you now associate it with a signature vector, so that instead of counting the total number of alternating trees that you encounter during the algorithm, you just count the total number of signature vectors that you encounter. And for that idea to work, you want this map to be injective. So you don't want two alternating trees to have the same signature vector. So what we do is we say that every time we make a change to the state of the alternating tree, the value of the signature vector, the lexicographic value of the signature vector actually decreases in each iteration. So this would then mean that the map is injective. Just to give you an idea of how the signature would look like, it's just a pair of numbers. I don't want to get into the details, but just to give you an idea of how the signature looks like. So signature for the whole alternating tree would just be a concatenation of these integers corresponding to the signature of each layer. And the final step is simply we bound the total number of possible signature vectors by a polynomial. Okay. So this is a very rough sketch of the analysis. So the only thing that you need to prove is, each step. But so this is the sort of the key thing that you need to see, and after that, sort of most of the things follow. All right. One interesting thing that I want to mention is the polynomial bound of the signature vectors is curiously we obtain using a bound on the partition number of partitions of an integer which was found by Hardy and Ramanujan in 1918. So, which says that, so the partition of a natural number n is the total number of ways you can write n as the sum of natural numbers without regard to order. And what they showed, Hardy and Ramanujan, was that this function p of n, which is counting the total number of partitions of n, is growing like 1 over n times e to the square root n. And actually, so the number of coordinates of the signature vector is going to be log n, because we concatenate the signature of each layer, and the total number of layers is log n. And each coordinate of the signature vector is also going to be log n. This requires a little more thinking, but okay, if you accept that, then you can think of each signature vector as simply a partition of some number of size at most log square n. And then if you just plug it here, then you get the polynomial bound. But the bounds are really bad, but if you fix r and epsilon, then you get a polynomial algorithm. So that leads me to the next slide, which is, can you obtain a polynomial dependence on r? Sorry. Right. Yeah, I did not. So let me just skip to, right. So imagine, so the only thing the algorithm needs to succeed is this claim, So let's assume that in a particular, when you build a new layer, this is actually smaller than or equal to constant times that. Then the collection of S vertices is simply going to be all the vertices in the alternating tree which have fewer than u addable edges. And the hitting set, or one hitting set for the collection of all the edges incident to these vertices, is just the collection of all the b vertices in your alternating tree. So the, yeah. Okay, so currently the algorithm has an exponential dependence on both r and 1 over epsilon. Now, if the algorithm had a polynomial dependence on 1 over epsilon, then it would really constructivize Haxell's condition. This is easy to see. So if an algorithm worked only assuming tau of s is greater than 2r plus 3 times s minus 1, then it would also work when you set epsilon to be 1 over polynomial in n. Okay. So sort of, yeah. So this is a very interesting question, and there is also so one reason that this is interesting is, of course, okay, this is a result in, I mean, it is a constructivization of a problem which we did not know before. But another reason why we are working on this is also that it has the potential to constructivize results, for example, also in approximation algorithms. So for example, this problem, restricted assignment minimum makes span scheduling. For this problem, the assignment LP is very well understood. We have a 2 approximation, and the LP also achieves this integrality gap. But we know that the configuration LP is strictly better in this case by a result of Ola. So, but this result is not constructive. So the question is, these ideas, so these constructivizations, can you use to give better algorithms in this case?